All right, so now we move on to lesson 8 of relations and functions, and it's dealing with domain and range in both interval notation, and then in part B will be set notation. Well, right away, let's define a couple really important things here. Domain refers to all the x values that are for any given relation, and then the range is all output values or y values that are valid for any given relation. All right, so let's look at the first type of relation we can possibly have, which is discrete relations or discrete relationships. Discrete relationships list an x for each given y, and they use curly brackets in order to list these terms for each value. Now, values should be listed from smallest to largest always, and then if the value appears more than once in a set, it should only be listed once. That's something really important to note. If it's listed more than once, it should only be listed once. So we look at the example below and we say, okay, well, if we're given the relation of these ordered pairs, 1, 3, 2, 4, 5, 6, then our domain is all the possible x values. So what we would do is we'd go, okay, well, 1, 2, and 5 represent my x values. So I put the curly brackets and I list out 1, 2, 5, and then close the bracket. Similarly, I look at my y values for my range and I go 3, 4, and 6 are my range values or the y values. And because it's discrete or just specific points and not continuous data, we know that we would just put it in brackets in these curly brackets and we would list our 3, 4, and 6 in numerical order. Now we're going to do the same thing with the next example. What I want you to realize is that we have inputs or our x values on the left and then our outputs or our y values on the right. When we put this in domain or specifically set notation for this discrete data, what we're going to do is say domain is equal to curly bracket, and I'm going to list out all my x values in numerical order. So 2, 4, and 5, close bracket. I then do the same thing for range. I go range is equal to, and now I want to look at my outputs or my y values, 3, 4, and 5. There we go. Okay, now we look on this next example here and we realize it's a bunch of discrete points or specifically ordered pairs that represent specific values. So what we're going to do on the graph right away is we're going to fill in what those values are. So in the first one, I have 2 and 5, or I should specifically say negative 2 and 5. My next point would be 1 and 3. I then have an x point, or point that crosses the x-axis. This is an x-intercept. We say it's at 4 and 0 for vertical height. We then go down to 1 and negative 2. And then finally, we have a point here at negative 3 and negative 4. Now, this is discrete data because we're just describing a bunch of points that are in the Cartesian plane, and they're not connected by any lines, so they're not continuous, they're discrete. Domain, I'm going to list out all the possible x values here. Well, right away, I see that we have negative 3, which is the smallest x value, then negative 2. Then what I want to pay attention to here is, look, we have 2 1s for our x values. Thus, what we're actually going to put here is just one of those 1s and move on because we don't want to repeat the same value. And now we say 4 for our last value here. Range, we're going to put all the y values for each of those. So my first y value, or the lowest value, would be negative 4, then negative 2, then 0, then 3, then finally all the way up to 5. Okay, now last example in this specific set, we have 1, 1, 1, 2, 1, 3, 1, 4. What I want you to realize is that all the x values are actually the same values, and these are discrete points that appear in the Cartesian plane. Now, here's a bit of a challenger. What type of shape does this line make? Because if I was to look at this, or what type of shape does this discrete data make, I would look at this and be like, okay, well, if it's 1, 1, then I could plot 1, 1 somewhere about here if I was to guess. 1, 1, then 1, 2, then 1, 3, and then 1, 4 would obviously just be a touch higher. What are we actually doing? We're describing a relationship that's vertical. And a vertical relationship, if these were connected points, would be undefined. So if this was describing a continuous data plot, well, and we drew a line through it, we'd be saying this is a vertical line with an undefined slope. But for this example, we just want to say that our domain, there's only one possible x value, and that is 1. And remember, we don't want to repeat it 4 times. We're just going to put it 1 time. Range is equal to, okay, well, I'm going to go 1, 2, 3, 4, because that's all the possible y values in numeric order from least to greatest. All right, now we introduce a little bit of continuous relationships. Continuous relationships, instead of listing the coordinates, we give the endpoints of the relation. And then we always want to give the smaller endpoint first, then the larger. Now, here's a differentiating factor. We use square brackets if the endpoint is included in the relation. And what we're going to come to know is that when it means included, if I was to put this in terms of inequalities, it's going to be greater than or equal to or less than or equal to. And that will be more involved with set notation, but we're going to tie that concept together of saying if it's square bracket, it's included, meaning if I was to do this in set notation, those are the symbols I'd use. And then opposite to this would be if it's a round bracket, the endpoint is not included. So it would be strictly greater than, strictly less than if we're talking about our set notation. But for now, what we're going to do in this lesson is our interval notation. Okay, and then for relations with an endpoint of infinity or no endpoint, we use negative infinity, positive infinity, and we're going to always use round brackets. Okay, so we look off to the side here and we consider the following examples. If I'm looking at the domain, I'm thinking, how far left does this graph go? How far right does this graph go? So right away, domain, I go to an absolute minimum of -4, and it's a hollow dot, meaning it's not included. Thus, I have to put a round bracket. I then go to my farthest right point on the x-axis and say, well, that's 3, and 3 has a solid dot, so it is included. And here's what I'm going to do off to the side here as well. We want to add a solid dot means included, a hollow dot means not included. Okay, domain here of our next example, or actually we should do range first before we move on to the next one. So our absolute minimum value, where does that occur? That's at x equals negative, or y equals -3. It's a solid dot here, thus a square bracket. And we go as high. This is the highest y value, and that occurs at 4. Because it directly crosses through 4, we know this is a square bracket, meaning it's included. Okay, domain of our next one. If we look at this, it infinitely extends out this way and to the right. So if these infinitely extend out, that means it could go all the way here, all the way here. Are there any restrictions on the domain? No, they actually stretch out to negative infinity with a round bracket and positive infinity with a round bracket, because we know these arms could go out to infinity this way and then out to negative infinity to the left. Range, we have a highest possible point here. Our highest possible point is at 2. Our lowest possible point, well, these graphs continue to extend down infinitely in both directions. Thus, the lowest possible point is negative infinity, and we would put a round bracket. Our highest point is 2, which would get a square bracket because it is included. Now, something to note, it's always minimum to maximum. Regardless of its the domain or the range, it's always your minimum value to your maximum. Negative infinity is considered a minimum value. This is our maximum height. Domain, minimum, which is a negative infinity. Maximum, which is positive infinity. All right, so let's go through a couple examples here and all their differentiating parts. We want to do interval notation for these because part A of our lesson is interval notation. Even though we did a little bit of set, we want to primarily look at interval like our last example. So when I look at the first graph here, or the first relation, I'm thinking, okay, how far, and I want to describe it in terms of domain, how far left does this graph go? Well, we would say that is at a value of -3. How far right does it go? That's at a +3. And because it crosses through both points, we would say that our domain in interval notation is -3 to 3 with square brackets because those endpoints are included. Range, I then go, okay, my minimum occurs at -4 because it drops as low as -4, but then it goes as high as +3. And so because it crosses through at both those points, what I'm going to do is say my minimum range is -4, or the lowest y value. The highest value is 3, and then they both get square brackets because it's all included. Now, next example, how far left do I go? Well, I go all the way out to here, which is -5, and then my maximum value occurs at 1 here. So when we do our domain, we're going to do square bracket -5, comma, 1, square bracket, because when we look at our endpoints, they are solid dots, and solid dots mean they are included. Okay, now we look at our range. The lowest possible y value occurs here at -4. The highest value occurs at 2. So when we do this, we're going to do square bracket -4, all the way up to a maximum of 2. And there's square brackets for both because remember, they are solid dots here. Okay, our next example, we look at our domain. Well, our domain, it looks like when in terms of this arrow here, that means it's going to extend out to infinity in the negative infinity direction. So when we talk about our lowest point, it's always going to be, well, negative infinity with a round bracket because we put a round bracket when we deal with positive or negative infinity. But furthermore, this arrow indicates it infinitely extends out in the left direction towards the negative infinity direction. Now, what is the maximum x value? If we look at this, the maximum x value occurs at 2. It's a solid dot, thus meaning it's square. And so I say 2 and close the bracket. My range, the lowest possible y value here, occurs at -2. And because it's a solid dot, I'm going to put a square bracket. Now, how high does this graph go? Well, if this line infinitely extends in this direction, we know it's going to extend to positive infinity. And thus, I'm going to put positive infinity here. And infinities always have round brackets. All right, and then now with our last graph, we have something that extends left and right to infinity and negative infinity. And so when we talk about the domain, there's actually no restriction on the domain. It includes all the infinities. So it's negative infinity to positive infinity. And remember, infinities have round brackets. My y values, we can see that it's infinitely extending in the upwards direction and then infinitely extending in the negative infinity direction. So my range is the same thing. All right, interval notation, let's do that again for example 3 here. So if we're looking at the domain, we wanted to say, what is the lowest possible x value? Well, that looks like it's at -5. And there's a solid dot, meaning I'm going to put a square bracket, -5. And now I need to figure out what's the maximum x value. It occurs at 6 here. But because it's a hollow dot, we know this is going to be a round bracket because it is not included at that endpoint. Now, something that might help you visualize this a little bit better in terms of minimums and maximums, you could technically just draw a dotted line here or highlight a dotted line along the minimum and maximum. Now, we can actually do the same thing with the y values. What is the lowest possible y value? It occurs at what looks to be, well, the numbering is a little bit off, but we would say that this is at -6 down here. Now the graph runs through -6, so we know that it's going to be a square bracket, -6, comma. Now we look for the maximum y value, which looks to be at 2. And because it runs directly through 2, we're going to put a square bracket. Now, like we did with the x's, what we could do is highlight along the minimum, highlight along the maximum. And now what I want you to see is that, do you see how our graph is all contained within this square? Now all we have to do is say, okay, well, how low does it go? How high does it go? How far left does it go? How far right does it go? And express that in terms of x's. And then our final detail when we do that is just to say, is it included or is it not included, or vice versa? In this case, this is included, this is not included. Okay, let's look at our next graph here. We have a graph that extends upwards to positive infinity, downwards to positive infinity, or to negative infinity. But then what we have is this open point here. What we actually call this is a point of discontinuity. This is what we call a POD. A point of discontinuity basically says that if there's a hole in this graph at this point, we actually need to split our domain and range in specific ways. So it looks like we don't have a y value of 2 because there's a hollow point there and the graph does not meet there. So what we're going to have to do here is we're going to say, okay, domain, what is the lowest possible x value? Well, the x's start at 1 and it's a hollow dot, so it's not included. So what I'm going to do is I'm going to put round bracket 1. And we know that once it's past 1, it extends to positive infinity because it can continuously go right as far as we want. Now, in terms of the range, this is where it's a little bit different. The range, we're going to consider this in 2 different ways. I need to look at it from the point of view of 2 and upwards. Well, at 2, we know it's not included at 2. So we would say this is going to be 2 for y, which is surrounded by a round bracket. And then it extends up to positive infinity. But another piece of this range is to say, okay, well, our lowest point occurs also at negative infinity for this graph. So we're going to write in curly bracket negative infinity, and it goes as high as 2, but 2 is not included. And something you should notice here is that if I put round bracket and 2 is shared between those two things, but we see the round brackets here, it means that that 2 is actually not included in our graph. It just approaches 2, but never actually reaches 2 because of that point of discontinuity or the hole. Okay, now we're going to look at our graph here, our fourth one, and we look at this and say, okay, well, how far left does this graph go? And what I'm going to do is I'm actually going to do our containing method that we did before. I'm going to highlight along the x value of our lowest point, and then I'm going to highlight along where our positive x's go, but it looks like we have an infinite arrow this way. So it actually goes to infinity. And now what I'm going to do is do the same thing but for y's. So I realize my lowest point occurs along the blue here. My highest point, well, it extends out to positive infinity as well. So what I can do now is say, well, my domain, it starts at -4, which is not included because of the hollow dot. It's not included. So now I'm going to say this is -4 with a round bracket, and then it extends out to positive infinity, which always has a round bracket. My range starts at 1, and it is included because the graph directly runs through there. So we're going to say that this starts at 1 with a square bracket and then extends out to positive infinity because the height is uncontrolled here. It will just extend upwards in infinite direction. All right, so this is where you're going to want to check your understanding, especially dealing with interval notation. It can sometimes be a little bit tricky to start. How do you know when you do square bracket, round bracket, and then dealing with endpoints? How do you identify what endpoints mean what? That's a big thing with this. So make sure you're getting your practice here. All right, so now we go on to lesson 8b, which is domain and range in set notation. So set notation is just slightly different, and it takes our approach and just re-aims it in a little bit way. It basically says we can treat domain and range of any graph in, if I was to look at domain and range of any graph, it might look just slightly different in regards to the notation, but it technically means the same thing. So this is just another way to write domain and range that represents the same data. Okay, so a couple things with set notation. Set notation has a couple elements that we need to specifically outline. So recall, curly brackets are set notation. Remember, when we were using that discrete data always uses set notation or those curly brackets. And then with set notation, we can also use this notation to describe any sort of continuous function. So now we have two notations we can use for continuous functions, either set or interval, and either one is correct. Technically, if you were to show either way, that would be totally fine. However, when you go to exams or tests, they might try to show you multiple choice in interval, and then they might put one in set notation. Just know that going forward, interval notation tends to be a little bit more popular, especially at the 20 and 30 level. All right, let's do a quick review of inequalities. Inequalities talk about the relationship between two values, and specifically when we have a specific data above or below specific points in the Cartesian plane. So greater than or equal to, meaning included, less than or equal to, meaning included, and then less than strictly. Now let's actually look at a number line and see what this looks like. Consider the expression where x is greater than 3 and x is less than -2. What we're going to do right away here is draw them on a number line by going 0, 1, 2, 3, 4. And same thing in the other direction, -1, -2, -3, and -4. Now, what I'm going to do is I have to recognize that when we talk about something being strictly greater than, what we're actually saying is this is a hollow dot. It doesn't actually include 3, it's just strictly greater than 3. And similarly, less than -2, it's strictly less than -2. So when we plot these, we're going to use hollow points. Hollow point here, hollow point here. Now, if we're talking about x's that are greater than -3, we would have an arrow facing to the right. And then if we're talking about it being strictly less than 2, we would have an arrow going to the left. So there is our functions combined together, or specifically our mapping on this number line. Now, inequalities that include the value, we see that if they include the value, that means they're going to have the greater than or equal to or the less than or equal to, and if they include it, it's a solid dot on any graph. Now let's do the same thing here. We're going to put our number line together. So 0, 1, 2, 3, 4. Then we have -1, -2, -3, -4. And I'm going to put this on the graph all together. 3 has a nice solid dot here. -2 has a solid dot here. Greater than or equal to 3, we're going to have an arrow going out to the right, just like our previous problem. Less than or equal to -2, we have an arrow facing to our left. And there is our information plotted on the number line. So you can see that when it's strictly greater than or strictly less than, it's a hollow dot. If it's greater than or equal to or less than or equal to, it is a solid dot, meaning it is included. All right, so some notation that we really need to be clear on. Curly brackets are always used in terms of this notation. So if we're doing set notation, we have to be clear that it's curly brackets. It is not square round like interval notation. Set notation also has this such that symbol that you're actually going to see going forward a lot. Such that means that we're defining what a variable means in the context of any given problem. And then finally, element of, or this backwards E, says that it's a part of some number family or number system. So whether it's that 1 is a part of the whole numbers or -2 is a part of the integers, we could rewrite that and say that some value is a part of some number family. Okay. So now what we're going to do is we're going to do the domain and range in terms of set notation. And then what we might do is actually throw in interval notation just to show you that strict comparison. So I think about this example here, determine the domain and range in terms of the graph. So first of all, remember, domain talks about the minimum x value, the maximum x value. The minimum x value occurs here at +1. The maximum x value occurs at +infinity because this line would continue to extend. So here's how we do set notation. Domain, double dot, our first curly bracket, and now we want to go x such that with that vertical bar, and now we have to define x in terms of this problem. If x starts here and extends out to infinity, well, what we have is a hollow dot, meaning 1's actually not included, but once we get past 1, everything is included. So it's going to be x in here. X is greater than 1. And then once it's past 1, because it goes to +infinity, it could actually be any number in the real plane past that 1. So how do we express that? X is an element of the reals. So backwards E, R, where ER is element of the real numbers. Okay, now the range. We're going to do something similar here. The range, curly bracket, Y, such that. We want to figure out what the lowest value is and what the highest value is. Well, the highest value occurs at 7. The lowest value happens at -infinity because it keeps going down and down and down. So if the highest value is +7 and it's not included because of the hollow dot, we're going to say that it's y is strictly less than 7. And then once it's past 7, y can be any number in the real plane or any number in the Cartesian plane because this is a continuous line. Now, if we were to do this in terms of interval notation, here's what it would look like, and I'll do it in red below. We start at a minimum value for x of 1, and it's not included. So we would say domain is round bracket 1, and it extends to +infinity round bracket. Our range, well, it reaches a highest point of +7 and a lowest point of -infinity, but remember, it's always lowest value to the highest value, and because 7's not included, it has a round bracket. So there's a direct comparison of interval versus set notation, where this is our set notation, and this is our interval notation. Okay, let's do a couple more examples here. So determine the domain range of this graph. Well, in the 20 and 30 level, you're going to get really good at identifying what type of graphs these are. This is some type of square root of x graph, where y equals the square root of x, and it might have some transformation on it, which we don't need to know for this year, but going forward, you may get really comfortable with identifying what graphs are what. Now, domain, we're going to put d double $, semicolon, curly bracket x, such that. And now we want to identify the x value that represents our minimum x value is 1, 2, 3. So we're at -3, and it's a hollow dot. Once we pass -3, it extends out to +infinity. So how are we going to express this? Well, it must be that x is strictly greater than -3, And once it's past 3, it can be any number in the real plane. Range, double dot, bracket y such that, now what's our minimum y value? It occurs here, which is at +1. So if we're at a lowest point of +1 and there's a hollow dot, it means y has to strictly be greater than 1. But then we know once it's past 1, it can be infinity because it keeps going up and up and up. So we're going to say that y can be an element of the reals only if it passes y is equal to 1. Or more specifically, once the graph gets past this minimum value where it's not included, it can be any number in that plane. Okay, interval notation again. Domain, our lowest value is -3 and it's not included, so it gets a round bracket. Infinity always has a round bracket. Our range, well, range, it occurred at a lowest value of 1, which has a round bracket because of the circle, and it goes as high as positive infinity, round bracket. Yet again, set notation, interval notation. All right, another example here. Domain and range, we're going to start off by writing our domain statement, domain, semicolon, curly bracket, x such that, and then now we need to determine the minimums and maximums. Well, the lowest x value occurs at -24. That's how far the graph goes. And now the absolute highest point is x equals 0, or right along the y-axis. But here's what's different about our graph this time. It doesn't extend out to infinity in either direction. We have a contained graph. So what I could actually do here is, if it's a contained graph, I could just draw dotted lines along my lowest and highest x values. And then I could do the same thing with my y's. My highest y, my lowest y. And do you see how the entire graph is contained within that square that we've outlined? Now all we have to do is say, okay, well, x is contained between specific values. X is contained. What values is it contained between? Well, the minimum value is -24, and the highest value is 0. Now, if it's a hollow dot and we want to use inequalities, we strictly say that x is greater than that -24 because it's moving this way or in the right direction. And then once we're at 0, it moves in the other direction, or it pushes back. So we kind of get this push-pull motion of forward and back containing the function. Thus, x must be less than 0, but also greater than or equal to -24. And then once it's between those values, it can be anything in the real plane. All right, now we go to range. Similarly, squiggle y such that we're going to put y in the middle, and because it's contained between two values, the minimum is y is equal to 0. The maximum is y is equal to 12. And now we think, okay, well, if it has to be something in comparison to 0, y must be greater than 0. It's above. We get this kind of push action vertically. But then once we're at 12, we get this push down vertically. And so it kind of contains this function. So y must be less than 12, but greater than 0. Once it's in this interval, it can be any value in the real plane once it's in that interval. Now, yet again, we can put interval notation here and say domain. Our lowest value was 24, and it was not included because of the hollow dot. -24. My maximum is 0, and it is included, or sorry, it is not included, I should say, because of the hollow dot. So I put a round bracket here. Range for my interval notation. This is going to be, okay, if the lowest point was 0 and it wasn't included, I'm putting a round bracket 0. The highest point was 12, and yet again, it's not included because of the hollow dot, round bracket. So if you were to compare set and interval notation, here's a pattern you should notice. If I put a strictly less than and a strictly less than like these, or I should say in the case greater than and then less than, what you'll notice is that this symbol corresponds with a round bracket. If I was to put equality here, it would have had to been a square bracket. So there's that pattern. If you see a strictly less than, strictly greater than, it must be that these are round. Whereas if it was greater than or equal to, these would have to be square. All right, and then one last problem before you are encouraged to do your own practice here. So describe this in terms of domain and range. Well, let's start off with our domain. Domain, double dot, x such that. Okay, now we're going to look at our graph here, and what we're going to do is realize that it doesn't extend out positive infinity or negative infinity. So what we're going to do is we're going to try and draw a box that contains this. My least x value occurs here. My greatest x value occurs here. My greatest y value occurs up here. My least y value occurs down here. Now, what we should notice is that this line segment is contained within the box we just drew. So now what we're going to do is we're going to put an X in the middle and say, okay, well, if I look at the left endpoint or the left dot, we see it's a solid dot here. And if it's solid there, well, we're going to say that this is 1 and X must be greater than or equal to that 1 because it must continue to go this way, meaning the X values get more positive. How high does it reach? Well, the largest X value occurs at this endpoint, and that's at 7. But once it's at that 7, it must be less than or equal to that 7 because all the X values are then less. So we kind of get that push-pull action that I was talking about, where if we know the function is contained here, it has to go greater than 1, but then also less than 7. And then once we know it's in this interval, X can be anything in the real plane or the reals. All right, now range. We do the same thing, y, such that we're going to do the same thing where we put y in the middle. And now we need to see how low does this go? We'd realize it's down at negative 14. So if it's at negative 14 and it reaches the highest point up here of negative 2, then we're going to put negative 2 here. And then now we have to realize the endpoints are solid, meaning y must be greater than or equal to that negative 14 and then less than or equal to that 2. Same push-pull. It must be less than this negative 2, but then greater than that negative 14, containing this function between these two values. And once it's between there, y can be an element of the reals. Okay, for interval notation, domain. If the endpoints are included, it is square brackets. It's going to be 1, and my largest value is 7, square bracket. Range is going to be our lowest value is negative 14, our highest value is negative 2. And do you see the correlation here? Less than or equal or greater than or equal to? If it's greater than or equal to with that equal sign there, it's a square bracket, meaning included. Same thing with the range. Greater than or equal to, it's a square bracket indicating it is included. All right, this is where you really need to get your check your understandings in. Make sure you're trying both set and interval notation and you're comfortable with them. Like I've said before, interval notation is going to be a little more popular, but know how to do both because both may pop up.